talking about pressure, what is pressure? Okay, so it's a force that's exerted by something on something else, right? We're going to use very generic terms here. Okay, so when we're looking at pressure, you're talking about a force. When we're talking about the pressure of a sample, what you're actually looking at is the force on a specific amount of area. A really high pressure thing is going to exert a lot of force. Low pressure exerts very little force. Now, when we're talking about a gas sample, what are some of those factors that can influence the amount of pressure that are exerted by a gas sample? The area? Okay, and how will the area affect it? If you have a small area, what's going to happen to the pressure? It'll be higher, right? Whereas a larger area would be a lot less. With this one, I always like to draw the analogy of, would you rather have someone step on you with a high-heeled shoe, or would you rather have someone step on you with a tennis shoe? Which one of those would you prefer? Tennis shoe. Why? Why don't you want someone with a really small, high-heeled stiletto shoe to step on you?
Because it's going to hit you.
It hurts. Why does it hurt so bad?
Because it's sharp.
Well, it's sharp, but why does that little bitty heel hurt so much worse than a big tennis shoe?
All that pain is going to be one.
All that pressure's on that one point, that very small area. So that's kind of the analogy I like to draw there. When you have those concentrated areas, you have a lot more pressure over that area. Okay, so we have the area. What else? Heat. How does heat affect it?
It affects the particles, so they collide bigger with the particles.
So as things get warmer, they're moving. The average kinetic energy of those molecules is moving faster, and they hit those walls with more force, so you have a higher pressure there too. Anything else?
Not the volume, the actual amount of the particles.
The number of moles, right? Yeah, the numbers of the particles and atoms, yeah. So as you increase the number of atoms and moles, you're going to also increase the pressure as well. So there's a few things that can affect it that are variable in there. And these are actually what we're going to look at with equations today. Okay, how many of you guys read that part about the straw with the 10.9 meters? Kind of interesting, huh? Maybe. We're not going to talk about that, but... Okay, so the first thing we're going to do that your textbook looks at is something called the kinetic molecular theory. What is the kinetic molecular theory? What is it trying to do?
Predict the correct behavior for most gases.
Predict the behavior of gases. So the kinetic molecular theory is basically trying to give you a way to be able to analyze what's going to happen with gases when you do certain things to them. So there's 4 parts to the kinetic molecular theory. What's the first part of the kinetic molecular theory?
Is the gas a collection of particles?
Gas is a collection of particles?
Yes.
In constant motion.
Okay, everybody awake this morning?
Well, I think it's basically 14 like the assumptions of the 4 parts.
Yeah, they were like the same thing.
They're kind of the same thing?
Yeah.
Okay, just shout out what you think. Okay, so that's the one. What's another part?
They only collide, they don't repel.
They only collide. There is no repulsion. What else?
There's a lot of space between particles.
And lastly,
The speed.
okay, so those are the 4 parts of the kinetic molecular theory. Now, when we talk about the assumptions that are made, they do kind of go along with this. So one of the assumptions is that there is no interactions between the neighboring gas molecules. As they say, there's no repulsion. This is flawed. There is some attraction and repulsion there because you have things that, when we start talking in chapter 12, we're talking about intermolecular forces, and that will go over this what we call a dipole moment, where there actually is an influence of charges in gases. So that is an assumption that there's a very little bit of air introduced to it from that, but it's so minimal we just kind of ignore it in here. There is a lot of space between them. That is kind of, but once again, as you get larger gas molecules, then you have interactions occurring because they're taking up more space. So there's a few little flaws with it. However, purposes, we pretty much ignore them. We don't really talk, I don't think we talk about the van der Waals equation in here too. I think that's 150. So that's the kinetic molecular theory. All right, continuing on, we're going to look at pressure in a little bit more detail now. Pressure, what are some of the units that we use for pressure? Actually, first, how do we calculate pressure? Okay, and like we said, the larger the force over a small area, you're going to have a much higher pressure. What are the units that we see for pressure? Atmospheres, what else?
Torr, PSI.
Torr, pascals, PSI,
Millimeters,
millimeters mercury. There's also inches mercury you can see as well. Some people use that. These are just some of the units of pressure. There's a ton of units of pressure. Now, PSI, that should be one that's familiar. Why do we know PSI? I hope you've checked the pressure in your tires at some point in time in your life. Yes. It's a good idea to do that if you haven't. Yeah, so that's pounds per square inch. That's what we use for our automotive tires, bicycle tires. That's PSI. What about atmospheres? Where do you see that? Weather. Yeah. Sea level, what is the pressure at sea level supposed to be?
14.7 PSI or 1 atmosphere.
1 atmosphere. See, I wouldn't even know PSI. I need 1 atmosphere. Yeah, so at sea level, the pressure is supposed to be 1 atmosphere. That's kind of the standard of where they get that from. And let's see here, millimeters mercury. Anyone know where you see that one? Barometers. Yeah. What does a barometer do?
Oh, the weather, the density in the air?
The atmospheric pressure. Yeah. Barometers measure atmospheric pressure, and they use millimeters mercury for that a lot. And also inches mercury, depending on where you are. So those are kind of where they use some of those units. Pascals, I'm trying to remember. I don't know that I've actually ever really seen that commonly used. Is it on some tires too? So we tend to not use that one that I know of very much. Okay, so those are kind of the units there. You do need to know how to do the conversions. I give you guys conversion factors for these. I don't make you guys memorize these. The only one that you should know is between atmospheres and torr and millimeters mercury. Those are between millimeters mercury and atmosphere, and between torr and atmospheres, it's the same. Does anybody remember what those are off the top of your head? 760. 1 atmosphere equals 760 torr, which also equals 760 millimeters mercury. So those you need to know. The rest of them I will give you. I do not expect you to memorize the more obscure ones. Okay, so the conversions here. Let's look at this first one. We have 45.23 torr, and we're trying to go to atmospheres. So for my conversion, we just wrote down what the equivalence is. What's going to go in the bottom down here? 760 torr, and what's going on the top?
1 atmosphere.
1 atmosphere, and how many sig figs should our final answer have?
4.
So our final answer should be that. Any questions on that one? So this is a pretty basic review of Chapter 2 right now, basically. You should be able to do these things in your sleep by now. Hopefully you're not dreaming about it.
Ms. Stickers, on that, can we leave it like that or put it in
You can put it in scientific notation if you want to.
Okay.
Yeah, that's up to you. Okay, any other questions on this one? All right, the next one, we have 25.345 pascals, and we're trying to convert to PSI. Just like before, there's probably several different ways of doing these. The conversion factor I happen to look up may not be what you use. You might have done multi-step. I just did a 1-step. I didn't do this with my textbook. I just looked up the conversion on my phone. So if it's not what you use, don't panic if you get the same answer. How many sig figs should our final answer have?
5.
So you should have gotten somewhere around that for your
Yes.
PSI. If it's off by like 1 or 2, what on the last decimal, that's fine. I mean, we might have slightly different conversions depending on where we picked them up from. Any questions on this one? Okay, so conversions. Remember how to do them if you don't. Now what we're going to do is talk about a series of laws that govern behavior of gases. So there's a bunch of relationships that they've determined with gases, and so we're going to go through a lot of these relationships at a fairly quick pace. Because like I said, these are mostly like algebra. Here's A, B, C, D, solve for C, kind of a thing. So Boyle's law. What is Boyle's law? What does it relate?
Volume of a gas and its pressure.
Volume and pressure. And what do we see the relationship between volume and pressure is?
Inversely proportional.
It's inversely proportional, which means what?
If one goes up, the other one goes down.
You increase one, the other one decreases. So you have Boyle's law mathematically stated is that if I increase the pressure, I'm going to decrease the volume. If I decrease the pressure, I increase the volume. So there's the opposite relationship there. Where's a place that you might see this in your real life?
Scuba diving,
Scuba diving? Swimming?
airplane. If you're
Where else? Airplanes, the ears, right? Ear pressure? Yeah, we all love that. Babies love that too. What else? Going up to the mountain? Driving through the pass every day? When I get here, I'm like, what? Okay, so there's some good Boyle's law that we see in a daily basis. Now, when we're doing these calculations, one of the nice things about Boyle's law is we do not care what the units are for pressure or volume as long as they're the same on both sides. So you don't have to do any funky conversions for Boyle's law. You can just plug in your volume, plug in your pressure. If they're the same on both sides, you're set. If they're not the same on both sides, you have to change one so that you do have the same thing on both sides. But that's the only type of conversion you have to do. So our first problem here, we were told that we have a gas that occupies 12.3 liters at a pressure of 40 millimeters mercury, and we want to know what the volume is when the pressure is increased to 60 millimeters mercury. Now, when I'm solving these problems, what I recommend that you do is I recommend that you make a list of everything that is given to you. So this way you know what equation to use. Because as we go through today, we're going to be learning several different equations. And you can kind of use the process of elimination. So I would look at this and I would say, okay, I have a gas that occupies 12.3 liters. 12.3 liters is what? Is that pressure, temperature, what is that? Volume. 12.3 liters is a volume. So you're going to have to look at the units. So we have our volume, initial volume, 12.3 liters, and it has a pressure of 40 millimeters mercury. This is my initial pressure. So my P1 is 40.0 millimeters mercury. And then it says, what is the volume when the pressure is increased to 60 millimeters mercury? So that 60 millimeters mercury, I'm told that it's increased to it, so I know that that's my final volume, my second volume. So my pressure. Got me misspeaking now too. So P2 is 60 millimeters mercury. And I'm trying to solve for V2. That's what it's asking me about. So I can look at this, I see I have pressures and volumes only, I'm going to be using Boyle's law. So I just plug these in. To my equation, and then I have to solve for V2. How do I solve for V2? I have to get it by itself. How do I get it by itself?
Divide the 60.
I divide both sides by my P2, right? So I have to divide both sides by the 60 millimeters mercury. V's cancel out. Over here, my units cancel out, and I'm left with liters for my unit, which is what I want for volume. So my V2 in this case should have how many significant figures?
3.
3. So I'm thinking it's 8.20. And well, the calculator probably only put down 2, because I have 8.2 scribbled on my notes real quick, so they probably only put down 2. Okay, questions on this one? Now, I do not go over arranging these all the time. So this is I do it once for each equation, and that's it, because this is algebra. You should know how to do that. So if you get lost because of it, you need to go get some help with the tutoring, because they can help you with that. All right, any other questions on this one? Now, do you think it's important to keep your units as you're doing these calculations?
Yes.
Very important, because if this was given to us with 2 different units here, I would see my units didn't cancel, and I know I have to do a conversion. So make sure you keep your units as you're writing these problems out. Okay, this next one, we have a gas at 25 degrees Celsius occupies 3.6 liters at a pressure of 1 atmosphere, and we want to know what will its volume be at a pressure of 2.5 atmospheres. So what of these variables am I given this time? Do I know my V1? What is V1?
3.60 liters.
What is P1? Do I know it? And do I know P2? 2.50 atmosphere. Do I know V2? No. So that's my unknown there. Now, the 25 degrees Celsius, do I care about that? Nope. So one of the tricks with these is figuring out what's relevant and what's not. So we do like to throw in useless information just to make sure you're paying attention. Okay, so for this one, once again, you're going to solve for it. We're solving for V2 again. So V2, remember we rearranged it to basically that. So it's going to be how many sig figs should our final answer have? 3. So 1.44 liters. Questions on Boyle's law? Fairly straightforward. Okay, the next one is Charles's law. What is Charles's law? Okay, so it's relating volume and temperature, and what is the relationship between volume and temperature? Directly proportional. So if I increase volume, what do I do to my temperature? Increase it as well. So what you do to one, you do the same to the other. So the relationship for this one should be that. Where's my now, with Charles's law, there's a caution that I give you. Anybody know what that caution is? Let me read my mind. All temps are in Kelvin. With gas laws, all temperatures are always in Kelvin. You always have to convert them to Kelvin. So let me say that one more time. All temperatures are always in Kelvin. This is the number one mistake on gas laws in exams, is that the temperatures don't get converted. So how do you convert between Celsius to Kelvin? Add 273.15 or 273. You know, that little bit difference won't make that much to me. So you need to make sure you do that. I do not give you temperatures in Fahrenheit and then have you convert to Kelvin. I always give them to you in Celsius. So there's always going to be a Celsius to Kelvin conversion. So just add 273, you're good. Okay, once again, volume can be in any unit there as long as it's the same on both sides, but the temperature has to be in Kelvin. We've talked about absolute zero in here, right?
Yes.
Okay, that's what I thought we had. All right. So, looking at these problems, our first problem here, we have 600 milliliters of air is at 20 degrees Celsius, and we want to know what the volume is at 60 degrees Celsius. So once again, I go through and I make a list of what I know. So that's 600 milliliters of air. What is that telling me? My volume, my initial volume, right? So I know my V1 is 600 milliliters, and it's at 20 degrees Celsius. So that tells me what? Temperature, right? So this is my initial temperature. And then I want to know what the volume is at 60 degrees Celsius. So 60 degrees Celsius is my final temperature. And I'm trying to solve for V2. So I just plug those numbers in and go, right? No. What do I need to do? I need to convert all those to Kelvin, right? So to do that, we just add 273 to both. Okay, so, I'm pretty sure that is 333, right? My mind isn't playing tricks on me. That number just seemed too nice. Okay, so to solve for this one, I'm trying to solve for V2. How do I solve for V2? How can I rearrange that? Multiply both sides by T2. So both sides over here get multiplied by T2. This rearranges to V1 T2 over T1. sig figs should that final answer have?
3.
3. So it's going to be 682 milliliters, is what I got. Okay, questions on that one? How's our algebra holding up? We doing okay? Okay, the next one. The next one, we have a gas that occupies 900 milliliters at a temperature of 27 degrees Celsius, and we want to know what the volume is at 132 degrees Celsius. So 900 mils is what? It's our initial volume. And the temperature of 27 is what? Is that T1 or T2? T1. And then T2 is 132 degrees Celsius. And we're trying to solve for V2. So what do I need to do before I can solve this? Convert to Kelvin. Yeah. I don't know why I'm having trouble with simple math this morning. Okay. So I have 300K from one, 405 from the other, and then to solve for my V2, it's the same equation as over there. So this would just be now, how many sig figs should that have?
4.
That should be with the decimal written right there. 3. So this is going to round to what?
1, 2, 2.
0.
Yeah. Okay, questions on that one? All right. So far we've looked at volume and temperature. Oh, if I were to have to rearrange this, let's say I wanted to solve for T2. How would I solve for T2?
Would it be V1 times
This one throws people a lot.
Oh, salt 14.
So I have to multiply both sides by T2, right? So when I do that, I get this, right? So now what do I have to do to get T2 by itself?
Multiply T1.
Multiply both sides by this, and then divide both sides by that, right? So my T2. So your algebra probably needs a little bit of refreshing on that one, maybe. Make sure you remember how to do that, because I do tend to sometimes ask those. I kind of assume you should know how to do any of these conversions. So, okay, questions? All right, going on then to the combined gas law. What is the combined gas law? What two gas laws does it combine? Boyle's and Charles, right? So what do you think it relates? Pressure, volume, and temperature. So it relates all of them. So we kind of get the big picture when all of those change. So for our combined gas law, so there's our combined gas law. Doesn't matter what units these are in. Okay, what does pressure have to be in? Any as long as it's the same on both sides. So pressure doesn't matter. What about volume?
Milliliters.
I don't think it matters.
As long as it's the same on both sides. Doesn't matter. How about temperature?
It needs to be in Kelvin.
Kelvin. So that's the only one. Kelvin. So that's our big, once again. So these two, as long as they're the same on both sides, you're okay. If they're not, convert one of them. The temperature down here has to be Kelvin. Okay, and I think that, yeah, the first one I thought I remember doing a conversion. All right, so our problems down here, this is where those lists become more important, so you can really keep track of what you're dealing with. We're told that we have 2 liters of hydrogen originally at 25 degrees Celsius and 750 millimeters of mercury are heated until a volume of 20 liters and a pressure of 3.5 atmospheres is reached, and we want to know what the new temperature is. So when I look at my list, I'm told first that I have 2 liters of hydrogen. What is that going to be?
Volume 1.
V what?
1.
V1. So my V1 is 2.5
pressure.
And these are heated until a volume of 20 liters. So 20 liters is going to be what? B2. And a pressure of 3.5 atmospheres. So that tells me what? My P2 is reached, and we want to know what the new temperature is. So we're trying to solve for T2. So this is one of those arrangements that I was warning you about with how we rearrange everything kind of trickily. So when you rearrange this to solve for T2, T2 is going to equal that. So you should be able to rearrange it to that. Any questions on how I did that? Okay. So that's how I'm going to solve for this. Before I can solve for this, what do I need to do? I need to get my temperature to Kelvin. So this has to go to Kelvin. And then what else do I need to do?
Either change 3.50 to millimeters of mercury or 750 millimeters of mercury to atmosphere.
Right. I need to get these in the same unit, right? So I think on my notes, what did I do? I went to atmospheres. So I converted this to atmospheres. So to convert to atmospheres, you just divide 760 millimeters mercury in 1 atmosphere, and that is that many atmospheres. Okay, if you did it to millimeters mercury instead, you converted this one, that's fine. We should get the same answer, so don't panic. It's perfectly fine to do it that way as well. Okay, so once I have these, I now plug all these values into this equation up here. Okay, so I plug all those in and crunch the numbers, and then what is the answer that I get? I actually have my final answer here.
1,060 Kelvin.
What is it?
1,060 Kelvin. I don't know. That's what I got on my side.
I went to my final answer. I didn't write my in-between, so that was kind of stupid. Yeah, that number right there. Okay, so this is the number that I get. Now, I don't specify in here what unit your temperature should be in, but if you had to guess, what unit do you think those final temperatures are going to be reported in? Not Kelvin. Celsius, yeah. So whenever you're asked for a temperature, assume go to Celsius, because you're given it in Celsius, and that's what, do we have thermometers in the lab that can measure Kelvin? No, there are some, but we don't have any. So we always go down back into Celsius. So to convert from Kelvin to Celsius, what do I do? So when you subtract this, you end up with that. Now, how many sig figs, based upon our numbers up there, should this final answer have?
3.
3. That's what we have lots of them with 3 as the fewest. So this is going to round to that. Okay, questions?
Why did we change from Kelvin to Celsius?
This initial temperature was given to us in Celsius, and with gas laws, we always go back to that same unit. And temperatures, we always measure with Celsius thermometer in the lab, so that's why we go back to Celsius as well. Yes?
So how do we get back to Celsius?
You just subtract 273 from the Kelvin
from the
temperature.
answer.
Yeah.
Okay, I have another question. For the pressures on this type of problem, they're always supposed to be the same unit?
You always have to have them as the same unit, yeah. So, and like I said, did any of you go convert this to millimeters of mercury?
Yeah.
Did you get the same answer? No. Yeah, you should get the same answer. So unless there's something really off in the math, you should get the same answer.
If you don't convert it to Kelvin, would you still get
If you just run it as Celsius, no. Yeah. I've tried just to see what would happen. It's pretty far off.
So for the conversions, we have to go to Kelvin, and then for the final answer, we go back to whatever was given to us, basically?
Yeah. So temperature, if I ever ask you to calculate temperature, just know, calculate it in Celsius.
Okay.
Yes.
You gave us the problem already in Celsius.
Correct. I give it to you in Celsius, and I want the final answer in Celsius. But you have to convert it to Kelvin. Because remember, we're talking about addition and subtraction, not multiplication and division here. So like, if you don't do this addition operation, you would be multiplying stuff by a lot less of a value. So you have to do this right here. It's not the same thing. If you try to just plug this in without doing the conversion to Kelvin, you're going to get a very drastically different answer. 886 is what you got by not doing it. Yeah.
So it's like moles, basically.
Yeah.
To run it through there.
Yeah, kind of like that. So it does. Trust me, it doesn't give you, as we saw, the same answer. It's kind of fun to play math games like that. Yes.
Is it a problem like that, like, you know how it's already asking for Celsius? Could it be asking for Kelvin and then we have to convert it to Celsius at the end?
At the very end, we don't typically do that. I don't think I've ever actually seen a gas law problem where they give you the temperature in Kelvin already. They're always giving to you in Celsius. Yeah. Just because I said that, you'll go in your book and you're like, look, there's one. Other questions on this one? Okay, let's look at the second one. The second one, we have a gas that occupies 900 milliliters, so at a temperature of 27 degrees Celsius, and we want to know what the volume is at 132. Oops, wait, sorry. Wrong page. Sorry about that. I'm like, wait, this is too easy. Okay, a gas balloon has a volume of 106 liters when the temperature is 45 degrees Celsius and the pressure is 740 millimeters mercury. We want to know what its volume is at 20 degrees Celsius and 780 millimeters of mercury. So we're told that we have a volume, our V1 is 106 liters, and the temperature is 45 degrees Celsius, and the pressure is 740 millimeters mercury. And we want to know what the volume is, so we're trying to solve for V2 at a temperature of 20 degrees Celsius and a pressure of 780 millimeters mercury. So for this one, we have to rearrange that equation over there to solve for V2. So when you rearrange it, you should get that for your rearrangement. Any questions on how I got that? How's our algebra? We doing okay still? Okay, so remember, if you're trying to get rid of something on the top, you have to divide both sides. If you're trying to get rid of it on the bottom, you have to multiply both sides, right? So keep that in mind as you're doing it. Okay, so when you plug all the numbers in, oops. What do you need to do the temperature first? Convert. Okay, so for this one we have 293 there, and we have 335. No, 325. My goodness gracious.
318.
Thank you. Have you ever had one of those days where your math just doesn't work?
Every day.
All test day?
Every day.
Every day, yes. My daughter was up at 2 o'clock this morning, so I've been up ever since. Can you tell? That's when I wish I drank coffee. And P2 is 70. Okay, so here we have our equation and the variables all plugged in. And when we solve for this, how many sig figs should our final answer have? It should have 3. I don't know. I went to the final. Oh no, this is volume this time. It's not temperature. So our volume here.
Should be 4, right?
Isn't that good?
Going by volume?
3, because it's going off the first value number, right?
I'm going off the one with the fewest number of sig figs.
Of volume?
What?
Oh, yeah.
Right?
Yeah.
By volume, right?
I'm trying to solve for V2, right?
Yes.
And look at this right here.
Oh,
I
out
have
of all
four,
of them,
four,
out of all of
three,
them.
3, 4. So I go off of my one from
Okay.
fewest sig figs.
We thought it
I
was
was going by
like
volume.
your value.
Oh, no. This is just like all those operations we did before. You always go off of the fewest. So addition, subtraction is off of the fewest decimal places. Multiplication, division is the fewest sig figs. So yeah, we would have 3. Okay, questions on this one? All right, how are we doing on time? What time is it?
45.
45? Okay. All right, the next law we're looking at is Avogadro's law. What is Avogadro's law?
The
What
volume
does it
of
relate?
gas. And the
Volume
amount
and
of, the amount of the moles
the number of moles. How are those two things related?
directly proportional.
They're directly. Okay, so once again, when you do the one, you do the other. So we have V1 over N1 is equal to V2 over N2 is Avogadro's law. Volume, does it matter what unit it's in? No, as long as it's the same on both sides. What is N?
Moles.
Moles. So it's just always the number of moles. So the first problem here, we have 5 liters of a gas contains 0.965 moles. If the amount of gas is increased to 1.8 moles, what is the new volume? So if we make our list, we have our V1 is 5.00 liters. Our N1 is 0.965 moles. And our N2 is 1.80 moles. We want to know what V2 is. So to solve for V2 for this, it's going to be rearranged to that. So we would have this is our setup, and our final volume should have how many sig figs for our final answer here? 3, so we would have 9.33 liters. Questions on that one? Okay, now this one, we can have an additional step kind of thrown in there for this one. And it is when we're given a mass, not a volume. So for example, this next problem here shows you one of those. And we're told that we have a cylinder with a movable piston, contains 2 grams of helium at room temperature. And then we add more of that we add more helium at a constant pressure. And then we want to see what happens to the volume here, or how many grams are added to change the volume from 2 liters to 2.7 liters. So we know that our mass was 2.00 grams of helium. We know our V1 was 2.00 liters, and we know that our V2 is 2.70 liters. We're trying to solve for N2. This is related to N1. In order to solve for this, what am I going to have to do?
Grams to moles.
I have to get to moles. So I have to convert my grams to moles. How do I go from grams to moles?
Molar mass.
My molar mass, which I find where?
Periodic.
Periodic table, right? So I look over at helium. I see that helium has 4.00 grams per mole of helium. So I have 0.500 moles of helium as my initial, my N1. So for now, I can solve this. So I'm trying to solve for N2. So to solve for N2, that's going to be rearranged to this to solve for it. So this gives me my number of moles of helium. I don't have it written down. And I should have 3 sig figs because everything up there has 3 sig figs. So that's my moles of helium, but what does the problem actually ask for? Grams of helium. So I have to go back and calculate from moles to grams. So I have to use my molar mass again. So I'm going to multiply this one times my grams, and I should get approximately additional steps. So kind of went back towards that stoichiometry a little bit here. Questions on this one? Okay, are you guys starting to see why it's kind of important to write that list over here so you can kind of keep track of what you're doing as you solve these problems? I really don't recommend trying to dive into them unless you get really comfortable with these. Okay, the next thing we're looking at is the ideal gas law. The ideal gas law, what is it?
It just kind of combines all the variables into one equation.
It combines all the variables into one equation. When we're looking at an ideal gas law, are we trying to see what happens when we change a set of conditions like we have up to this point? What are we doing with the ideal gas law?
It's assuming that all pressures are constant, or that they're all ideal, I guess.
It's looking at how a gas will behave under ideal conditions. So what we're doing with the ideal gas law is if we know a set of conditions, we can predict what something else is going to be. So it relates pressure, volume, temperature, and number of moles. If we know 3 of those, we can figure out what the other one is. And it assumes that we're operating under ideal conditions. Okay, so in the ideal gas law, we see something called R. What is R?
Wait, 0.821 liters times atmosphere over mole. Okay.
Okay, that's its value. What is it, though?
It's a constant that never changes.
It's a constant that never changes. Why do you think there's a constant in there that never changes?
That's the ideal, I guess. The deal atmosphere.
How many of you like graphing? Should I even enter this topic?
No.
Okay, I won't enter this topic. Never mind. That's R.
Now we're serious.
Next question.
Okay, so this is R. This is a constant. It never changes. These units are very important because you don't want to get the units all mixed up as you're doing things. So I recommend that not only do you memorize the number, you memorize the units. Important to know. Ideal gas law equation. PV equals nRT. P is pressure, V is volume, N is number of moles, R is this constant, and T is the temperature. And what unit is that temperature in?
Kelvin.
Kelvin. If you notice R, what is the temperature unit in R? Kelvin. So if you use degrees Celsius, it's wrong. Okay. You should, once again, be able to rearrange this equation to solve for any variable as well. So it's just like the other stuff so far. So typical ideal gas law problems. We have how many moles of gas are contained in 890 milliliters at 21 degrees Celsius and 750 millimeters mercury of pressure. So once again, we make our list. We have 890 milliliters. This is our volume. We have 21 degrees Celsius as our temperature. And we have a pressure of 750 millimeters of mercury. Now, with the ideal gas law, do we care about the units of everything other than temperature? Yes, because R is a constant and it had units of liters, atmospheres, moles, Kelvin. We have to have our units in liters, atmospheres, moles, and Kelvin. We can't use anything else. So I need to convert this one to liters. How do I convert milliliters to liters? Just divide by 1,000, right? So I have 1,000 milliliters in 1 liter. Gives me 0.8900 liters. My temperature, I have to convert to Kelvin. And then my pressure, what do I need to put my pressure into?
ATM, but it's
I need to get in the atmospheres, right? So I know that there's 760 millimeters mercury in 1 atmosphere. What's that, 0.98? Okay, so I do all my conversions. That's probably the hardest part right there that most people mess up on. And then you just plug them into this equation. So I'm trying to solve for N. That's my unknown. So to rearrange this, N is going to equal PV over RT. So it's my pressure times my volume divided by R. And my plug all those numbers in, and then how many sig figs should your final answer have?
3.
3. So it's going to be, and we can just solve for it in.
I do too. Yeah. In front of the 3, you have 0.0364.
0 point. I might have missed a 0 when I wrote it down. Yeah, I missed a 0 when I wrote it down. There's 0 there. Okay, questions on that one? Okay, the next one. We're trying to figure out how many moles of a gas would be present. Am I looking at the right one? Yeah. In a gas trapped within a 100 milliliter vessel at 25 degrees Celsius and a pressure of 2.5 atmospheres. So once again here we're solving for N. That's our unknown. And then we have our volume is 100 milliliters. Our temperature is 25 degrees Celsius. And our pressure is 2.5 atmospheres. What am I going to need to convert before I can run this problem? Volume and temperature. So my volume is going to be 0.1 liters, and my temperature
298 Kelvin.
298 K. My pressure is fine. So I'm solving it the same way I did over there, and so it's just my pressure times my volume divided by R. And divided by T. And how many sig figs should that final answer have?